It's 2:30 in the afternoon. You've had lunch. You've gone through 4 other sessions. Let's all take a moment and recognize we're all falling asleep right now. That's okay. This is a great talk to fall asleep through. Great one here. If I can get a sense of my audience, I would like to, I'm going to, please humor me. I know we're engineers. We don't want to play games. I'm going to ask you to play a quick game with me, if we can. By raise of hand, when it comes to channels, not routines, not functions, when it comes to channels in particular, if you feel like you are a master guru of channels, I'd like you to raise your hand at this point. I got a couple of brave ones, okay? We're good. If you feel like if you were asked to talk about channels in an interview and that would cause a mild panic attack for you, you can raise your hand. Okay, we're doing good. Now, lastly, if you are here at this conference and you've never heard of the word channels before this talk, can you please raise your hand? Great, not television channels, by the way. We're at Go channels. Great. We're going to hopefully, for those who are gurus, I'm sorry. It's going to be an okay talk at the end of the day. For those who are in that in-between phase, just know that those gurus are making you do their work at the end of the day. So for the gurus, you knowing this makes it easier for them to write your unit tests. But for everyone else, this is just for you to get some more information on channels here. I'm so sorry for the camera guy. I will promise not to wander. Okay, I've already got a thumbs up. He's okay, great, because I'm a wanderer. I apologize. We're going to talk a little bit. I happen to have the benefit. I finished a master's degree in computer science, which some of you feel like is probably a waste of my money and time, but I did. In particular, a lot of my emphasis was on computer science education, which is even more of a waste of time and money. But I happened to work underneath a professor by the name of John Edwards, and he developed a program referred to as Fanon. That is programming Hanon concepts. Hanon is a piano concept. If you ever did piano and you had to do keys and you had this Hanon book, that was a concept that he took into programming. And in his major studies, he broke down the idea of when he teaches programming, we would separate programming language syntax from computational logic. Those are 2 separate core elements of education. To explain what I mean by that, you may all notice this kind of looks like a function, but it's missing something. Let's play another game. What is this function missing? Parentheses, thank you. I love that. We're all playing Dora the Explorer right now. Don't worry. Okay, we got another one. What is this one missing? It's missing a curly brace or a bracket or however you guys want to call it in this case. This one is missing its brother right there. It's missing the bottom one. What is this one missing? This one's a little trickier.
Test.
I heard 7 different ways of referring to the keyword func. Good job. That you all got it there. Now this one, what are we all going to call this? Identifier. The identifier, they technically refer to this as the alias. That is the alias of the function here. Absolutely. The way Fanon worked is you would do 100 exercises like this. Write a function from scratch. What is missing? What is that? And you drill into these students the syntax of how to write a function. And then, after all that is done, you come to class and you learn conceptual logic. What is reusability? What is parameterization? What is encapsulation? Cohesion, abstraction, modularity, all of that wonderful Gang of 4 stuff that we pretend as Go engineers doesn't exist. Because to reference Gang of 4 means that Java exists as a language. If you don't know what the Gang of 4 is, raise your hand. Okay, I officially feel old, and I come from the Java world, I'm sorry. At least I came to Java before I went to Go. We are going to talk a little about programming language versus computational logic. Realistically, programming language syntax is how to write an application. Computational logic is when to use a particular tool versus a different tool at the end of the day. I firmly believe whenever you have been taught channels in the past, it is only ever focused on syntax. It's all the syntactic sugar in the world. How to do an unbuffered channel, how to do a buffered channel, how to do a read-only channel, how to do a write-only channel. And no one in their right mind would ever tell you why, or when, or what is the purpose of this, or what is the purpose of that. My talk will cover zero syntax. We are only talking computational logic, so that by the end of this talk, you know when to use a channel and when not to use a channel. And if you know those core concepts, guess what? You can talk to everyone else on their AI tools and they'll tell you how to do the syntax. Or Google, or this old thing called Stack Overflow. May it rest in peace. We're gonna cover 3 concepts: asynchronous writes, asynchronous reads, and asynchronous reads and writes. Now you might think that's redundant, and it's not. So we're good. We're gonna talk about what is a write. So let's go into core functional logical concepts here. In channel logic, a write is whenever a system publishes data to a queue. So realistically, I've got a channel, I'm getting data written into it. However, let's broaden the context of a write to be everything the system does before it gets to a channel. It's all this different logic here. So think of it as let's write it this way. So I've got a write, I've got action A, which leads to action B, which leads to action C, leads to action G, and that results in a write to a channel queue. Now I'm calling this a something because we're gonna get into some more details about that, but let's just consider all of this concept. These are a write, all combined together, resulting into a write to a queue. So what is a read? Well, a read is when the system takes data off the channel. But let's broaden that concept too to everything that happens after the data comes off the channel. So, we've done all the write actions, they've led to the queue being published to, and now we're doing action W, action X, action Y, and action Z. Now, some of you have studied a lot. And this might look like a pattern you are familiar with in the past. It is called event-driven architecture. It is the process of something, a write, also known as a publisher, leads to the processing of a queue, and then a read is a subscriber pulling data off of that queue. That something is our event queue. Now, this is a hard question. Who in this room has never at all worked with a queue beforehand? Okay, great. We're in good hands. Who's worked with SQS, SNS, all of that stuff before? Okay, how about Kafka?
Yeah, let's talk.
Okay, what about Kinesis? Who's worked at all with that? Okay, let's think. What are some of those? RabbitMQ. Okay, what are some of the other bespoke ones you all love that I don't know about?
Gnats.
I'm sorry, what? Gnats?
Jetstream.
Gnats?
Yes.
Like NATS?
Yes.
Okay, great. I feel really ignorant. That's great. What else have we got that I missed?
Tomorrow.
Whoa, I really need a microphone. One at a time, please. Loud.
Async.
Async. Okay, what else?
NSQ.
NSQ. Okay.
Temporal.
Temporal. I heard one over here.
Redis streams.
Redis streams. We've all worked with queues, right? Channels are just in-memory queues. That's it. Talk done. You now understand channels. That's it. Thank you. Yeah, then right there. We'll go a little more detail. That's all they are. And all of this other read, write, buffered, unbuffered, it's all syntactic sugar to get the queue to do specifically what you want. But as long as you keep in mind, these are just in-memory queues, the complexity goes out the window. Now, I want to demonstrate some channel logic in a code, maybe show you a couple of things you never knew you could do with channels, and I want to do one important thing. I want you to take the idea of a routine, and I want you to throw it out the window. Channels can exist without routines. They are things that are independent. Do they work with each other? Yes. Do you ever think to use a channel without a routine? Probably never at the end of the day. But it's the same way of like, we treat queues as this, like we have, like you guys all defended gnats, like I was an idiot. And this is a queue, but like if I told you gnats could exist without a Go server, well, you're like, duh. Of course, it's a queue. Channels can exist without routines. They just serve the routines. They serve the service at that point. So we're gonna build a system called, we're gonna basically create an in-Go version of SED. I want you to all do me a favor, and if you've ever heard of the program, the CLI tool SED, please raise your hand. Okay, everyone who has not, please raise your hand. You've never been a DevOps engineer, and I'm sorry. That's just life. SED stands for Stream Editor. The main thing you're ever gonna use it for is most likely search and replace. You literally type in a command that's like SED, and you hand it a regex string that you copied off of Stack Overflow. Or you used whatever AI tool you're all using to have it generate for you, and it will do a search and replace for you. By the way, if you have not noticed at this point, I do not use the AI for hardly anything. I'm a fundamentalist by nature. I train way too many engineers on these fundamentalists to ever want to trust AI to do this for me, because I just feel like people should know this crap. We're engineers. That is the point of engineering at the end of the day. So, but if you're all AI focused, that's totally fine. You can all silently judge me or loudly judge me, however you feel like. We're gonna build a synchronous system. Now, I'm gonna show the basics of this system. There's a bunch of like little fluff to make it easier. I have built a struct here. I almost called this a class, and I almost got persecuted for that. I have a struct here that is basically just a struct to gather arguments off of the CLI, and then I have this idea of a file action. A file action, in this case, if you notice, it has 4 elements. We have a directory, a find, replace, and a name. This is the idea of our event that is going to be occurring within the process. And then I have a read function, a write function, and a main. And we're just gonna briefly look at main here, pretty straightforward. Is this big enough for everybody? Is lighting okay? Can everyone read this pretty well? Okay, good. Within our process here, we're basically just doing a basic log to put out our arguments. I am making a buffered channel. Almost all these are gonna be buffered channels. It doesn't matter at this point. Just think of this as a queue with a maximum capacity of 300,000 items, which is a massive channel, by the way. I'm just gonna let you know that. We're gonna write everything, and then we're reading everything, and then we're running with it. So that's all main is doing. Let's talk about what this write is accomplishing. So this is pretty straightforward. SED, the way you can do it on an individual file, but you can also do it on a directory. So you will notice if you read this, this is recursive logic. I'm so sorry. That's just how it is when you're going through directories. What this does is it basically says read a directory. If, for all the files in said directory, if it's a directory, go read the next level of directory sort of thing. If it's not, dump a file action on the queue. It basically says, I found a file, there's a file action needed. This doesn't even know what the file action is. That's been handed down to it. It just knows, hey, I'm gonna be doing some sort of file action. Actually, it's not handed down to it, it's generated. But it effectively, in this case, let's abstract file action just being some sort of event. In this case, it's search and replace, it could be other things. So if it's a file, dump it on the queue. If it's a directory, go on down. If you notice here at the very top, every time it starts, it prints out a D. That's really fun for our logging, where it's gonna be like, if it's a D, we found a directory. If it's a period later on, we know we found a file. So that's all write is doing. Write is doing the pre-processing. It's all these actions that lead to a queue event. When we go to read is basically the exact opposite. Read is saying, go to the queue, read off the data, and do a read with it. All we're doing right now on a read would be a period. We could do a search replace on that individual file, but the idea is we don't care what happens before we get to the queue. We don't care what happens after we get to the queue. We're just focused on that stinking channel, which, as we all know now, is a queue. It's a queue. That's it. So, in this case, we're doing this all synchronous. By the way, don't know if you know this, you can make a channel, write to it, read from it, and never do a single asynchronous process whatsoever. In this case, you will have noticed, write is just a recursive algorithm going down into the files in the directories. Read waits for the writes to be done. That's why we're closing the channel right here. By the way, if you ever do this synchronously, you must close the channel before you read from it. Does anyone know why?
Blocking.
Because it will block. It will get to this read, and you're doing a loop over everything, and it's gonna be like, great, there's no more data. What do I do? This will stop the system. So if you're gonna do this synchronously, you have to say, hey, channel, you're not receiving any more data. That's all a close is doing, is just saying, hey, queue, you can't get any more data. You're done. But the data that's already in it stays there. You're not closing the memory. You're not closing it. You're just saying it is no longer writable to said queue, but you can still read from it. Does that make sense? So I create the channel, write everything, do it, close it, and then read it. So what does this look like? If you remember right, we said earlier, all of the Ds are directories, and all of the periods are files. So naturally, we get this world where we get a bunch of, it's so many directories, I didn't even see it. But you guys all saw the Ds fly by, and now we've got a bunch of periods. So that is a synchronous version of using a channel, not using a single routine, just purely channels at the end of the day. So let's talk about the first example. Would we ever really use a synchronous channel? No, it doesn't make any sense. You could do this in way more effective ways at the end of the day. The benefit of a channel is asynchronous nature. Now, I happen to, like I said earlier, to have come from, I started my prima lingua is JavaScript. I know, so hard. Yep, we got a little JavaScript user there. My second language was PHP, which I immediately abandoned. And my third language was Java. Now, if any of you have ever worked with a thread executor, debate on whether it's executor or executor or whatever, it's not a Pokemon. If you ever had to use with an asynchronous queue in Java, like an asynchronous like array, it is misery. Genuine misery. That was like a full-time job of my life for a month. Like, that's all I did. It was the worst. And so, like, the fact that we can just write this channel and write through this whole process, one of the main things of what you would do with the channel is what I refer to as an asynchronous write. We've seen a synchronous write and a synchronous read, but now we can do an asynchronous write where we spin off a Go routine to write to our queue, but we're still doing synchronous logic to read from it at the end of the day. So we go back to here, we go to our async write. All of our files are practically the same. The major difference is, if we look at main.go, let me pull this down, is that we start a wait group. Now, we're not discussing wait groups today, we're just discussing channels. Just know that wait groups are, I don't even know how to describe it, like the redheaded sibling of channels. Like, you need it, it's part of the family, but like, you don't really want to talk about them at the end of the day. So in this case, we create a channel, we create a wait group, and we start our asynchronous writer. This is still recursively going through our directory here, but what it does is that every time it gets to a subdirectory, it starts another channel. And then it can just go through everything. So you're no longer synchronously going through the whole file process and putting it all in. However, right now, we are still waiting for that writer, those asynchronous writers, to finish. We wait for the wait group to say they're done. We close the channel, can no longer receive any more writes, and we start reading it synchronously. That code is the exact same. So in the same way we had before, and if I come up here and I now have to cd over to our async write, we run the same command. We're still going to get a bunch of directories first and then our files, because the writing process was async, but the reading was still synchronous. So let's ask a stupid question. Why would I do this? Why would we write to a channel asynchronously and then read from it synchronously? I've got a bunch of examples I can give, but I want to hear from all of you guys first. What examples can you contrive why you would write asynchronously a channel but only read it synchronously? Any thoughts? Carson, yeah.
If you had like data gathering that took a long time, processing was fast.
Yes, data gathering took a long time, but processing was fast, yes.
You have a singleton pattern where you only want one thing to do the action.
Yep, singleton pattern, so like one thing to actually do the action, but a whole bunch of stuff to aggregate that in terms of processing. Any other thoughts? Yeah, I got one in the back.
You don't need to lock the writes.
Yes, okay. What do you mean by that? Keep going.
Well, if I have a bunch of memory, I could like async read that pretty easily on anything. But writing, now I've got to like mutex and stuff. And that
Yes,
data.
absolutely, 100%. I think a bunch of the things I put in here are, hey, I've got a database ETL, and like I am doing a bunch of upserts or updates. I don't want to keep track of collisions. I just want one connection to the database, and maybe I've got 1 million records, but they're all in updates. And so like they're gonna go fast, they're gonna be okay, but I don't want to have collision situation. There also is a world of like, how many of you have a problem where you get too many connections to your database? Like, who's ever had that problem? I certainly have. Like, so you want only one database connection, so that means post queue, I want to make sure I'm only doing one. There's also worlds of like in-memory modification. If I'm mutexing a bunch of files, I don't want them all occurring at the same time. Maybe there's gonna be a collision. Maybe there's transactional processing. Maybe I want to make sure all of my changes occur in one big batch group. And if they all don't occur, I don't want any of them to occur, sort of thing. There's also processing time. Maybe my read off of the queue is trivial. It's whatever. It's what Carson talked about. It's like it's very minimal, but getting the data takes a while. So I want to batch async that. So we've talked about now asynchronous writing. Let's look at asynchronous reading. This is the exact opposite at the end of the day. So I have an async read. Main looks very simple. So in this case, which this is really odd, if I am going to do an asynchronous reader, I must do that process before I start my writing. Because what's going to happen is it's going to like, if you start your writing and do all that and then do your reading, well, you're still essentially running synchronously because you've done all of your writes in a synchronous fashion. And then your reader's like, you start it and it's like, well, great, fine, but I'm going to still run asynchronously here. So you start your wait group, you tell it, hey, go read off of this queue asynchronously. I don't care what you're doing. I've got in this case, I do have a buffered channel because I don't want to kill my system. And then I start my writes in a synchronous fashion at this point. So as you all might guess, once I start this, our writes and even though our writes are synchronous, the reads are going to be asynchronously, meaning we're going to see dots and periods running at the same time because as I write to the queue, it's going to be reading it at the exact same time. So let's see if I can CD again with one hand. And this is my async read. So we're getting all those at the same time as they're coming off the channel. Once again, let's ask the question, why would I do this? Why would I want to read asynchronously off a channel, but write to it synchronously? What are your guys' thoughts? Got a hand, yes.
So we wanted, so it can be used when we want to run and read and write concurrently, but not too much concurrency.
Yes, this is a main one. Maybe you've only got, you're on an older machine, you got 8 gigs of RAM sort of thing, and you want to make the reading process like as concurrent as possible, but I really want to save all that CPU power for that process. I saw a hand here and then a hand here.
Matt,
Memory efficiency, yeah.
Memory efficiency, love it, yeah.
It's a web crawler, and you need to be really careful about how much you hit the website.
Oh, I love that. I don't know if you heard that. He said a web crawler, like maybe the website has a DDoS or it has a limit or whatnot. And so I want to read carefully, but I can do whatever I want with it as fast as I want at the end of the day. Yeah. I had a bunch of these. Maybe you have a database ETL. So like as database ETL, you've got a bunch of CSV records to be inserted, but it's all in one big file. You're not concerned about insert collisions, yes?
We have to define ETL for everyone. Not everybody knows.
Who doesn't know what an ETL is? Okay. Thank you. I appreciate it. ETL is an old-timey word for extract, transform, and load. It refers to the idea of I get data from one place, bring it over to here, and then bring it to someone else. We now modernly refer to this as a data engineering pipeline or things like that. I still lived in the days where I literally just write one application to just like grab a bunch of data, put it on my local computer, and then dump it somewhere else, sort of thing. Which is not great, by the way. Don't do that.
Don't do that.
Ever. Again. Maybe you have this world of like, I want to do that. Maybe I'm doing processing time. My write times are trivial, but my read times take hours, sort of thing. Maybe you have computational limitations. You guys called all this out. Okay, last of all, we've seen asynchronous reads, we've seen asynchronous writes. Let's do them together. So in this case, we have async both. This one, pretty straightforward. It can get pretty easy to get lost in the weight groups here. I have two weight groups. One is a read weight group, one is a write weight group. That is harder to say than it should be. In this case, I've gotten my arguments. You can do this without weight groups. This was just easier for this presentation to do it in this way. In this case, you start the reader, same way as we did beforehand, add in a read weight group, and then I start the writer. The writer goes through and writes everything to the channel, and then I wait for the writer to finish. I close off my channel, and then I wait for the reader to finish, because it's very possible your writer is finished writing, but is your reader finished reading? No, you got to wait for both of those things to be done, or else then you get a bad ETL that you don't write on your local computer. So we're going to come back into here, and we're going to come up, CD, async both. Great. And in this case, you notice, I don't know if you guys saw this, but there's going to be this world where like you're going to get batches of Ds and then batches of periods. It's going to be like this world because they're both going at the same time. So we're going to get a bunch of like big globs of it. But it always ends up at the very end that the writer is heavy at the first, and then the reader is heavy at the end. As it's going through things. You're going to see very few Ds here, but at the beginning of the file, you slowly, as you progress up, see more and more Ds as it goes through it as a directory. So, to finish off here, when would you do both async read and write? Anytime you have the computational power to do it at the end of the day. It's now a memory management task. How quickly do you need to get the data? By the way, most of your modern web servers or data engineering pipelines, they're using a variation of this concept, maybe just not on one local machine at the end of the day. So webhooks, I want to decouple the receipt of data from the processing of said data. I have a webhook, I receive it, I need to respond instantaneously to said webhook, so I just drop it in a queue. And then I say to a webhook, yeah, I'm good. And then some asynchronous reader picks it up and runs with it, sort of thing. Maybe I have a web server. I did this a lot in the past where I had a web API that needed to return an application ID. Basically, you're doing a process that you know is going to take longer than 200 milliseconds. So you have an API, receives it, you say, great, here is your ID of your thing that I'm creating. I put a record in for that, and then I throw it into a queue, and it's great, I'm gonna get to it asynchronously when I get to it, sort of thing. That is our world of eventual consistency. This is frequently seen in live data. I once built a tool where I had to read temperature data off of a vacuum chamber. So we had to read vacuum data and temperature data. And in that case, you start a live writer, like an asynchronous writer, to read it in, drops it into a queue. But I don't want what that is doing to be aware of I'm storing in a database and publishing it out sort of thing. You can use like a webhook or a WebSocket and like publish it into a database. So you have step differentiation of readers and writers there. So in this case, to summarize, let's separate the syntax of how we use a channel from when we use a channel. There's differences in that logic. And let's not get bogged down in our syntactic sugar of what a channel can and can't do. It's just an in-memory queue. It makes your life easier that way. And when we start thinking about because all of you have worked with events, if you start thinking your Go program like event-driven program, but all in memory, that's when channels start becoming really cool. Because you can get your publishers, which are your writers, your subscribers, which are your readers, and your queues, which are basically just your in-memory, your channels, which are in-memory queues. So, I think that is it. Any questions? I'm just glad I didn't, because it's snack time in 5 minutes. So, yes, hand here.
You didn't mention why your channel in the first example had to have such a huge buffer allocated to.
Such a great question. So why did I allocate 300,000 items to my buffer? Realistically, I was handing, the directory I told it to go to is my entire code directly, where I put all of my engineering files. That includes all of any JavaScript projects and node modules and things like that. So I basically, it's a buffered queue, but it's all synchronous. So the way synchronous works is you're gonna load the entire queue up, and then you're gonna tell it to stop receiving writes, and then you read from it. So you have to basically say, what is the max capacity of my node modules, which is stupid. And so that was why that was so big. Good question. I have a hand here.
Follow up on that question. Did you run into problems setting that number a little bit less than?
Oh, I started with like 100, and then I was like, I'm an idiot. And I think I even like tried right sizing it, and then I was like, what am I doing? And so I just set it to like 300,000. I just didn't, and it worked, and I didn't think about it anymore. Yes.
I live in files, and I deal with robocopy a lot. And when you're saying something back there about reading files and moving them, could this be used in a way to move between servers and keep I/O consistent?
Such a great question. The question being, in this case, if I understand correctly, you probably have like some volumes that you have an application that is like, I'm attached to this volume reading data and then attached to this volume writing data.
Really bad throughput.
With really bad throughput. I think anytime you have a single Go application that is doing things like that, 1,000% you can do things like that. Now the difficult part being is with volumes in particular is getting the application to know which one you're reading from, which one you're writing from, and all that. So like your I/O input is going to still be a struggle. But in terms of putting together the logical complexity of that problem, 100% channels are a great way of handling like, here's a thing, let me extract what I need to do versus what I'm doing with it. Does that make sense? You're separating the problem of identifying the problem. It's just like an event, like you just identify the event. So yes, I saw a hand really fast here. Is that in response to this question, or is this something else? Okay, I'm gonna go back here first and then here.
Well, is there a way in Go with the channels to do more like dynamic, like buffer allocation, like unbounded?
Yes, so I used everything. In my case, I called it a buffered queue, which is a limit on how to do it. You can do unbuffered queue. However, there are two rules with that. One, you must establish your reader and your writer You must establish your reader before you write to it, basically. Because what's going to happen is you're going to start writing to it, and it's going to try and dynamically grow in size, and it's like, I'm exponentially increasing, and no one's taking anything. And so it has an in-memory limit where it says, yeah, this is unbuffered up into a point that I don't let you do it. Kind of similar to the conversation about memory management earlier. So you can have it be whatever, but you must establish a reader before you write to it. Also to the point here, it is recommended to always buffer because the buffering is actually what bounds the context of how many readers you can have at a time. So if you unbuffer it, your system will just continue to like establish more and more and more readers until it maxes out your memory. We're at time. I'm so sorry.
It's fine.
Do you want to take the last one? Or you want to go on a lot of snacks?
Oh, we'll end here, but I'm sure you're gonna be around to answer more questions.
Yeah, absolutely.
Right?
I'll stick right here if you have more questions.
He'll be around this whole time. So thank you, Logan.